Today, I'll talk about functions in daily life. Before we dive into functions, let's talk about how things are connected in real life. We call these connections relations. A relation is simply a set of ordered pairs. For example, think about your friends and their favorite colors. You match one friend with a certain color or colors. This is a relation, and one input can have multiple outputs. But functions don't have exactly the same meaning as relations. Imagine a vending machine. You press a button, let's say button A1, and you expect a specific snack. If button A1 gave you a chocolate bar sometimes and soda other times, that machine would be broken. This leads us to the definition of a function. A function is a special type of relation where each input has exactly one output. Just like that vending machine, one button has one specific result. Let's look at this mathematically. Imagine two sets. Set A, our domain, and set B, our range. For a relation to be a function, every element in set A must be matched with only one element in set B. We write this as f A from B. If an element in A is left alone, or if it tries to point to two different outputs in set B, it's not a function anymore. Now that we know what functions are, we can explore their different types. In the rest of this video, we will see how these can appear in our daily lives through examples. Now, let's talk about the most common type of function we see every day, linear functions. The word linear comes from line, and that's exactly what their graph looks like, a straight line. Its formula is f of x equals mx plus n. But what do these letters actually mean in real life? Think about a taxi. The moment you get in, there is a fixed starting fee, let's say $5. This is our n value, the constant. Then for every kilometer you travel, the price increases by $3. This constant rate of change is our m value, or the slope. So if you travel x kilometers, your total cost is f of x equals 3x plus 5. Whether you go 5 kilometers or 50 kilometers, the relationship stays consistent. This predictability is why linear functions are so important in finance, physics, and even simply daily planning. Next is identity function. Its role is very simple. Whatever you put in, you get the exact same thing out. Mathematically, we write this as f of x equals x. Imagine a mirror. If you stand in front of it, the reflection you see is exactly you, not taller or not shorter. Or, in the digital world, think of a direct pass system. For example, if you're scanning your fingerprint to unlock your phone, the system compares your scan to the saved version. If the output matches the input, the phone unlocks. On a coordinate plane, this function creates a diagonal line. Both sides are always equal. Now let's look at the constant function. In this case, the output is always the same constant value, regardless of the input. We write this as f of x equals c. Think of an all-you-can-eat buffet. The price is fixed at, let's say, $10. It doesn't matter if you eat one slice of pizza or 5. The cost, meaning the output, remains exactly $10. The input, how much you eat, does not change the result. On a graph, this looks like a horizontal line. It has zero slope because there is no rise or fall. Whatever x is, y stays constant. Another type of function is called inverse function. If a function goes from point A to B, the inverse is its opposite, from point B to point A. Think about temperature. If you know the weather is 25 degrees Celsius, a function can tell you that's 77 degrees Fahrenheit. But what if you are in the US and see 95 degrees Fahrenheit on a sign? You need the inverse function to calculate that it's 35 degrees Celsius. To have an inverse, a function must be one-to-one, meaning every output comes from exactly one unique input. Visually, if you fold the graph along the diagonal y equals x line, the function and its inverse will match perfectly. What happens when you combine two different rules? We get a composite function, where the output of the first step becomes the input for the next one. Our formula could be f of g of x, so the output of g of x will become the input of f of x. Think about online shopping. Let's say g of x is a function that applies a 20% discount to your item. After the discount, f of x is a function that adds shipping costs. The final price you pay is f of g of x. You don't apply shipping to the original price. You apply it to the result of the discount. The order matters. Our last step is even or odd functions. An even function is symmetric about the y-axis. Mathematically, f of minus x equals f of x. Its graph is in the shape of a U. A real-life example is a satellite dish. Its shape is an even function, which allows it to reflect signals perfectly to a central point, regardless of which side the signals hit. On the other hand, an odd function has origin symmetry. If you rotate the graph 180 degrees, it stays the same. So, f of minus x gives you minus f of x. Think of a seesaw in a playground. When one person goes up, the person on the opposite side goes down by the same distance. Their positions are odd relative to the center. As a result, we can say that functions have a major role in our daily life, and different types of it can appear in many ways we actually don't realize.